In Super Paper Mario, after completing Chapter 4, you can now use the powers of the Pixel Fleet in Flipside. In the search for the fifth heart pillar, you have to flip this space rift that opens up a secret passageway. Following this passageway leads you to a room with 8 colored blocks, all initially turned off. Hitting each block flips the on-off states of a set of blocks. The goal is to turn on all 8 blocks, and doing so breaks the mirror and grants you access to the town of Flopside. When I first encountered this puzzle, I was just aimlessly hitting blocks trying to make things work, but I had to break out the pen and paper to realize that you had to hit each block once. But this still seemed like a pretty difficult puzzle for a kid's game, so after doing some research, wouldn't you know it, there's a sign on Flipside that says to do exactly this. So I guess I missed that. But that's not the end of the story. Hold on, roll that back. This solution only took 4 hits. Given that this footage is from a speedrun, this makes sense. Although it saves very little, like come on, 4 hits versus 8 hits, it does indeed save time. And as any speedrunner knows, every second counts. After doing a little digging, I realized that the Super Paper Mario speedrunning community learned of this information back in 2019, but the puzzle itself was referred to in a blog post back in 2009, so at least a few knew about this solution beforehand. Anyways, I thought it'd be interesting to dive into the math behind this puzzle and see why this is the case. So let's establish how the puzzle works. So we have 8 colored blocks and all of them are initially turned off. Now if you look at a certain block, like the red block, hitting the red block flips the states of the red, yellow, light blue, dark blue, and gray blocks. What we mean by flipping here is, let's say if the red block was on and the yellow block was off, then hitting this block would turn the red block off and turn the yellow block on. So this is an important distinction we're making here because we're flipping, not turning something all on or all off. We're only flipping states here. Now we can map out this flipping relation for all 8 blocks. Now it's a bit annoying to look at, so we'll convert this to a set of 1s and 0s. 1 means the block flips it, and 0 means the block doesn't flip it. This allows us to represent each block with a 0 or a 1. A 0 means it's off, and a 1 means it's on. Initially, all our blocks are turned off, so we represent them with 0s. If we hit the red block, we will flip some of these blocks on, since they're initially off. So we use 1s to represent flips. A block being flipped an odd number of times means it changes states, turns on in this case. An even number of times means it keeps the same state, stays off in this case. So if you hit the red block again, everything is turned off since we have flipped each block either 0 or 2 times. When applied to binary numbers, this operation is called XOR, which is represented by the symbol next to the red block. It goes place by place, or block by block in this case, and writes a 1 if they're an odd number of 1s, and a 0 if they're an even number of 1s. So XOR has 2 important properties. If you hit a block twice, it has no effect, since any block that's flipped is then flipped back again to its original state. Similarly, a number XORed with itself is 0. Furthermore, the order in which we hit the blocks doesn't matter, since the number of flips applied to each block is the same either way. So the order in which we XOR numbers also does not matter. We call this property the commutative property. So we have our 8 blocks and the 8 corresponding binary strings. We've already established that hitting a block twice does nothing, so the only way to yield unique results is either hitting a block 0 or 1 times. We've also established that the order in which you hit the blocks does not matter. So we want to count the number of subsets, which is the number of ways to hit these blocks. Well, for each block we have a choice. We can either hit it or not, and this choice is independent for a block. So if we multiply 2 times 2 times 2 all the way forward, we get 2 to the 8th, or 256 ways to hit the blocks. Now, there's not a lot of ways. You could test this in-game by hand and see which ways turn on all 8 blocks, but that's a bit tedious. So you can write a computer script for this, which is way easier. That's what the community did as well. And take the integer representation that corresponds to these 8 binary strings and test the XOR of each subset, since we established that equivalence earlier. And if that XOR ends up being all 1s, then we have our solution. And indeed we return the 2 solutions, which is the speedrunning method and the intended method. But of course, this is a bit overkill. But if you've been paying attention, you'll notice a neat pattern. each column has exactly 5 ones. So if we were to XOR everything, then we would get the result of all ones, which is what we want, so we want to turn on all the blocks. And this is the intended solution by the game. But what if it wasn't this easy? Well, for general n blocks, it takes at worst case n times 2 of the n operations, 2 of the n subsets to test, and we might be XORing up to n numbers per subset. So that's what this notation means. At the worst case, we have n times 2 of the n operations. For n equals 8, this takes pretty little time to write a computer program and run it for, but if we take n equals 50, for example, we get a lot of operations. And if you use the thumb rule that 2 to the times 10 to the 8th operations takes a second, this takes almost 9 years to compute. So surely there must be a faster way to do this. Now let's write things in a different but equivalent way. We'll define the variable xi to be 1 if block I is hit and 0 otherwise. Now, instead of looking at what a given block flips, we'll look at what flips a given block. So the columns we're looking at have now become rows. Well, we want an odd number of blocks to flip the block we're looking at, because that will turn it on. So we use the XOR operation, and we set everything equal to 1. And we want to solve the system of equations. But this seems tricky to solve off the bat. So what we're going to do is I'm going to convert this to something that looks a bit more familiar, addition. Since we're dealing with 1-bit or 1-digit numbers, this is the same thing as the XOR. If they're an odd number of ones, we return a 1. If they're an even number of ones, we return a 0. This is just saying we add up our numbers and we return the remainder when divided by 2. That's what the modulo 2 means. So let's ignore the modulo 2 for now and think of this as just regular addition. Now in school, you've seen systems of equations before. Usually we solve these over real values. Well, the way we solve these, at least for small equations, like 2 or 3 variable equations, is like we'll eliminate variables, isolate variables, solve for them, substitute back, and do that, right? That probably sounds familiar. Now, this seems a bit tricky to do with 8 variable equations. So you could still do the same thing, it's just a bit trickier. Luckily, there's an algorithm that kind of formalizes this procedure, so let's look into that. So what we will do is convert our system of equations into a cleaner form, a matrix equation. For the purpose of this video, think of a matrix as a grid of numbers, and a vector as a list of numbers. The left side of the equation has our matrix of coefficients and the column vector of variables. The right-hand side contains our column vector of answers. Each row in our matrix represents the coefficients for an equation, and we can recover our system of equations by multiplying the matrix and the vector. The way we multiply is we take a row vector in the matrix, take our column vector of variables, then we pair up the coefficients and the variables in the order they appear and multiply, and add the resulting 8 terms. Then we repeat this for each of the 8 rows. Here's an example of how we recover the first equation from this form. Now that we have this, there's one more thing we have to address, the modulo 2 which we have left to the side. Recall that modulo 2 just means that we're multiplying and adding integers and taking the remainder when dividing by 2 at the end. Now the equations that you've solved in math class are usually over real numbers or integers, and these are known as fields. The field is just a really strict way of saying that addition, subtraction, multiplication, and division all work reversibly. And the set of numbers 0 and 1 with addition and multiplication is also a field, denoted as F2. All that to say is that you can use the method of eliminating and isolating variables here just as you would do with real numbers or integers. For simplicity of explanation, I've hand-waved the definition of a field here, but I totally recommend checking them out as they're really cool. We're going to convert this to a more compact form called an augmented form, and we're just retaining the same coefficient matrix and target vector, and we'll label each column with the variable it corresponds to. So we can see that the equations, we can really just read them off row by row with the coefficients and the target. So now what we're going to do is we're going to use an algorithm called Gauss-Jordan to solve this. And it's really just a formalization of how you would eliminate and isolate variables just like you solve system of equations regularly. So the way it works is we're going to start by defining a pivot. So a pivot is going to be the first non-zero element in each row. We can use a pivot as a reference point to eliminate variables in all other rows or equations. The first half of Gauss-Jordan is called forward elimination. We will start with the first row, which we ideally want to have its pivot be the first entry, and then eliminate the variable x1 from each of the subsequent equations that have them. We can do this by adding the first row to each row that contains this, since 1 plus 1 is 0 modulo 2, or 1 XOR 1 is 0. Notice that this corresponds directly to just adding equations together normally, and so Gauss-Jordan just makes this a bit cleaner to handle. Now we have ensured that the first equation is the only one that has x1. We continue this process with x2. Notice we did not eliminate the x2 coefficient in the first equation. I'll get to why we do this later. The third row doesn't have x3 as its pivot. To keep everything in order, we can just swap rows, which corresponds to swapping equations. And we just repeat this process, right? We take the next pivot, and if we need to swap, we'll swap just to keep things in orderly fashion, and we'll eliminate subsequent variables. And you can see that we're slowly eliminating unnecessary variables in each of the equations. Alright, so we're getting close to the end here, and we're going to do x5. We'll do a swap here, upcoming. We're going to do x6. And then we get to, finally, x7, for which we just swap. But now you've noticed that there's no pivot entry for x8. It's just a 0. If a variable does not have a corresponding pivot entry, it's called a free variable. We can set its value to whatever, which is 0 or 1 in this case, and write the rest of the variables in terms of this variable. In other words, the value of this variable isn't forced. Now we can simply back solve for the values. Since for each row with a pivot, we will know the values of the variables ahead of it, so we can solve for the variable at the pivot position. This is why we didn't eliminate variables from the rows above the pivot, since it's not technically necessary. But for the sake of presentation, we can do the optional step of backward elimination, where we do eliminate variables above the pivot position. So you can see that we're basically doing the same procedure again here. So while this is running, I'm going to talk you through the definition of the rank of a matrix. After we've run the full Gauss-Jordan procedure, the rank of a matrix is simply the number of pivots. And in this case, our number of pivots is 7, so our rank is 7. We'll revisit the idea of rank later in the video. Now notice that for every variable that is a pivot, it's only present in the equation that it's a pivot entry for. Since x8 is a free variable, it still has floating entries. So now we can solve for our variables. We know that x8 is free. x6 and x7 have to be written in terms of x8, and they're in fact just equal to x8. x2 through x5 are fixed to be 1, as we can read off directly, and similarly x1 has to be equal to x8. So now we can plug in x8 to be 0 or 1. Plugging in x8 equals 0 gives us the short solution, and x8 equals 1 gives us the intended solution. And so just like that, we've shown that there are only two solutions mathematically, and we didn't even need to do any brute forcing here. But is this more efficient? That's the question we wanted to answer. If you remember for n blocks, the brute force method took, at worst case, n times 2 to the n operations. That's what this notation means. But what about for Gauss-Jordan? Well, for Gauss-Jordan, for each pivot variable, we had to eliminate the variable from at most n equations, and eliminating it from an equation took n operations because we had to add equations together, which had at most n variables. And so for each pivot variable, we had to use n squared operations. And we can have at most n pivot variables, so that takes in total, at worst, n cubed operations. So this is a world of difference. The brute force method takes exponential time, an exponential number of operations, while Gauss-Jordan takes a cubic amount of time. And of course, the left-hand side grows way faster as n grows larger than the right-hand side. So this is a huge win in terms of efficiency. So now, if you want any ideas for your next Kaizo mod, here you go. Here's something you can try. Now, let's cover some bonus content. We don't go too much into the weeds of mathematical definitions here, so we will cover stuff at a high level. If we take our coefficient matrix, each row represents which blocks, when hit, flip the state of block I. If we transpose the matrix, that is, make each row a column and vice versa, then each row represents which block that block I flips when hit. This is the form we were working with originally when we tried to determine which blocks we could XOR to the target state of all the blocks being on. Now what we can do here is we can apply Gauss-Jordan to this matrix, modulo 2, to create our pivot entries again. There is no target vector here, but that's fine. We can still do the same thing. We're still adding and swapping. The same procedure still applies. The result has 7 pivots, as you can see here, the sixth position doesn't have a pivot in particular. It's the same number of pivots as the original coefficient matrix, and thus has the same rank, 7, which remember is the number of pivot entries. So this is no coincidence. A matrix and its transpose do have the same rank, but for simplicity we will omit that proof in this video. What I do want to note is that the process of Gauss-Jordan gives us an interesting result. The resulting rows are linearly independent. That is, we cannot write any of these rows as the sum modulo 2 or XOR of a subset of any of the other rows. This is easy to see since each row is the only row of the bunch to contain its pivot entry. Like, for example, like the second row is the only one to contain a 1 in position 2. And we don't care about position 6 since it's not a pivot entry of any of the rows. Now, any on-off configuration that can be obtained by XORing some subset of the binary strings that represented the blocks from earlier can also be obtained by XORing some subset of these vectors. Since what we did here was we basically combined block effects to create simpler quote-unquote building blocks. Like for example, if you wanted to create the target state of all ones, you could just XOR all 7 of these vectors, right? And so the set of possible on-off configuration vectors is called a vector space. The definition of a vector space is a little bit more complicated. For the purpose of this video, over F2, it's a set where for any two vectors A and B, the set also contains A XOR B. So why do we care? These 7 vectors are special. We call them the basis of the vector space, which just means they are 1, linearly independent, and 2, specify the whole vector space. So that meaning that you could XOR any subset and get any on-off configuration you could get from the original puzzle. It's like kind of like how red, blue, and green can specify all the colors. Like you can't just do it with red and blue, but you also don't need red, blue, green, and yellow. Like the yellow is unnecessary. It's kind of like the minimal set of vectors that are still linearly independent, but also can get you any vector in the vector space. So any vector in this vector space can be written as the XOR of some subset of these 7 vectors. In fact, they correspond to a unique subset. So unlike when we had the 8 blocks earlier, there were 2 different ways to XOR to get the all-on state. There's only one way to do that here. You can only XOR all 7, and that's the only way you can do it. And the proof of this follows from the fact that they're linearly independent. It's not a difficult proof, so I'll leave it as an exercise to you, because it is a little bit of a fun proof. And now we'll finally end with one last definition. The dimension of a vector space is the size of its basis. So we have 7 vectors in our basis here, so the dimension of this vector space of all the on-off configurations is 7. Now there are 2 of the 7 different ways to XOR these vectors. We can either include them in our subset or we don't. And since each of the representations is unique, there are 2 of the 7 distinct on-off configurations you can get in the puzzle. But since there are 2 of the 8th total binary vectors of length 8, like you have 0, 1 in each slot, and there's 8 independent slots, this means that like not all configurations are achievable, right? 2 of the 7th is less than 2 of the 8th. So no matter how hard you tried, there was no way you could get all possible 2 of the 8th vectors from the puzzle. It's just not mathematically possible. This information will allow us to address one common misconception. I've seen this blog entry referenced several times when this puzzle has been discussed online, and it does a great job of covering what we've looked at so far. But it does make one false claim. It states that we can multiply by the inverse of the matrix on both sides. We in fact cannot do this, but let's look at what this means in the first place. For a matrix A that's invertible, if we take its product with its inverse, we get the identity matrix. Notice that if we represent this in terms of equations like we did earlier, it just reads x1 equals something, x2 equals something, and so on and so forth. So we can literally read the solution off from the target vector directly. So if this did exist, we could just multiply both sides by the inverse and read off the solution. However, the key word here is invertible. In fact, it ends up that our coefficient matrix is not invertible. And what does that mean? Well, we can treat A as a linear map. It takes us from one vector space to another by simply multiplying. For example, notice that the set of binary vectors of length 8 is itself a vector space, specified by the basis of 8 vectors. Literally in the identity matrix itself, you have a 1 each position. And it corresponds to all the possible ways we can hit the 8 blocks. So our coefficient matrix can take a vector of block hits and convert it to the resulting on-off configuration. If this matrix was invertible, we would be able to reverse this mapping, getting the vector block hits back from an on-off configuration. So for a mapping to be invertible, it has to be 1-to-1. But this is not the case for this puzzle, and we've already seen that before. There are two block hit solutions to the all ones configuration in the original Mirror Hall puzzle. This is because our matrix A has rank 7, so it takes a space with dimension 8 to a space with dimension 7. And so we're losing information, and there's no way for us to gain back this information by reversing the map, as multiple vectors can now map to one vector. Thus, for a matrix to be invertible, it has to be a full rank matrix, so that means that the rank is the same as the number of rows and columns. So only square matrices are invertible, and furthermore, they have to be full rank. So if you were to plug in our coefficient matrix from this puzzle into the inverse calculator, it wouldn't show up as invertible. However, as a blog post stated, you could still use Gauss-Jordan to invert a matrix if it was invertible. Since the reduced form will just be an identity matrix, you can use another matrix that logs your Gauss-Jordan operations, and that'll be your inverse. I'm not going to cover that in this video, but it's something cool to look at in your own time. Well, that about covers everything. Thank you for watching. I hope you learned a thing or two from this. I thought this is some really interesting math behind this puzzle. That'd be cool to share. And yeah, if you have any other video ideas for any other puzzles in Mario games or wherever, I'd be happy to cover them. Just shoot them my way. And yeah, thanks for watching.